Okay, thanks very much. Well, that sounds a little loud. I think I'm okay. So I am Andy Rudoff. I'm from Intel. But actually here, I'm not really here as an Intel employee. Instead, I'm really here as one of the founding members of the SNIA Non-Volatile Memory Programming Technical Work Group, or TWIG. That red line doesn't mean that I've been let go from Intel yet, but I just wanted to kind of make it clear that I wear two hats, and really I'm here with the SNIA hat on, and not so much the Intel hat on, although I couldn't help but to wear one of these little miniature Intel DC Optane modules on my shirt, but other than that, yeah. So every year we do this. This is actually the 8th summit, because we had 7 so far, and this is number 8. And every year I come up here and I talk about what the TWIG is doing. And I thought for people who are here for the first time, I'll give a little bit of the backstory. If you've been here before, you'll recognize. But I went through all of my previous talks from the past 7 years, which, believe it or not, we're still sitting on my laptop, though I need to organize my files a little better. And I pulled out what I thought was the key message each year, and you can see how it evolves. But first of all, just Jim touched on this, but the very rapid history here. In June of 2012, we started the TWIG. It was actually a small number of people from Intel and from HP got together and came to SNIA and said, we need to do a standard, a unified programming model. It was an immediate popular TWIG. Microsoft was there from day one. Red Hat was there from day one. VMware was there from day one. And a bunch of other companies. It's about 50 companies still are members of the TWIG. By December of 2013, we published the first Spec, the 1.0 programming model Spec. And then a couple years later in March, we published the 1.1. A couple years later, we published the 1.2 Spec. So it's had a kind of a cadence going along there. So right in between there, in January of 2013, we had the first summit. We called it the NVM Summit back then. Now we call it the Persistent Memory Summit, and you'll see why. And so I started with that 2013 summit, and I ripped one of the slides out of my deck. And the details aren't that important, but the slide basically shows that we were talking about being able to use NVM as standard block devices, but also it says in the middle there, NVM regions exposed as files. That was sort of already what we had in our minds. And then on the right, we were going to propose a new non-volatile memory API, a new asynchronous API, which you can kind of see over on the right-hand side. I drew in that same year some flows, and you can see in the middle here there is a flow that talks about memory mapping files. So that was, again, already in our mind. And then there were these new NVM underscore routines that I'm happy to say died off and never happened. So one less API in the world. Thank you very much. By 2014, we had published the first Spec, and so I started explaining what was in the Spec during this slot in the summit. And I started out by talking about what we called pm.volume, which was an in-kernel way of getting to persistent memory. And then on top of that, pm.file, which was the application way. Now, this is going to start to look pretty familiar if you've had any experience with our programming model, because you can see the application there going around the file system and just using the mappings that are set up in the MMU. That was really one of the key ideas of our programming model, and that's the picture from that Spec at the time. By 2015, I had taken that picture and revised it into the one that I have been using now for 5 years, where I took the management path on the left and made sure that that's kind of a first-class citizen, because it turns out to be pretty important. You can see the legacy path in the middle, the block path, and then on the right, our new persistent memory-aware file system path. 2015 was kind of a big year, because we had really solidified some of these ideas. We were starting to get traction with the operating systems. And since I am an Intel employee, in that same talk in 2015, I started talking about the instructions that you use that we've added to the processor for persistent memory. At least we've added it to the Intel processor. And you can see there are a few instructions up there for flushing stores out of the CPU caches. And then there's the second level of an instruction there called pcommit, which I'm kind of happy to say that a group of us, both within Intel and also a lot of Intel customers, thought long and hard about whether we really wanted to introduce this two levels of flushing, and we were able to kill pcommit before it actually ever shipped. Thank you very much. And actually, my partner in crime in killing it is actually sitting here in the second row. It was one of the funnest things I think I've ever done at a company, is to remove an instruction from a processor. So that was quite the experience. And also in 2015, we started talking about how to make persistent memory programming easier. And with that, we started coming up with libraries. This is the first, I think, presentation I did about the persistent memory libraries, which is now called PMDK. You're going to hear more about PMDK later today in a talk from the PMDK architect, so I won't go into too much detail right now. In 2016, we started focusing on all the traction we were getting in the operating systems, and so I just ripped a few of these slides out of the presentations. Neil Christensen from Microsoft came and talked about how Windows supports the programming model. We had Jeff Moyer from Red Hat talking about how Linux supports the programming model. Tom Talpe from Microsoft came up and talked about remote persistent memory, which we really started getting serious about. How could you do RDMA to persistent memory? What changes do we need in RDMA, and so on. And Tom's really been continuing to drive that in the years since this. Just due to scheduling and logistics and who was ready to talk about it, you'll see the Windows and the Linux in that year, 2016, but not VMware. VMware, we did have them front and center in the next year, 2017, where Rajesh from VMware came and gave a great talk about it. And actually, the talk right after mine, you're going to hear Rich talk about VMware's support for persistent memory even more. So that's pretty good stuff. And then also in 2017, I did my thing where I came up and said, what is the twig working on? And at the time, we were working on things like details around flushing. What are all the different types of flushing that you can do, and refining the error model and a few other things. And the flushing got kind of complicated when we talked about all these different ways of flushing things. There's the standard API like msync or flush file buffers on Windows. But there are these things that we called optimized flush, and there's kind of an interesting little thing in the middle, hidden in the middle of this slide, which most people aren't aware of these days, but this was only 2017, right? This is just a few years ago. It wasn't safe. The Linux community did not consider it safe for us to flush things to persistence from user space. So we had added those instructions, and we were all proud of these instructions. Look, we have this very optimized way of flushing things to persistence. And the Linux community said, no, we need the control point of you calling into the file system. And so I have this slide here that says on optimized flush on Linux is unsafe. You can't use it. And back then, our libraries in PMDK, we turned it off and we switched it back to calling msync, and they slowed down like 7x on some benchmarks. And we said we weren't gonna ship incorrect libraries. We're gonna keep them correct. We weren't gonna change this until there was a way of doing a safe flush. So stay tuned on that. On Windows it was safe, but not on Linux. That was a pretty interesting piece of our history. And then we also started talking about how to flush something on remote persistent memory, and that's the RDMA work with Tom Talpe that I mentioned earlier. The Spec also mentioned something called deep flush, which is a way of flushing to the smallest possible failure domain, and that's also has been available and shipping for some time, but also kind of a complexity that a lot of people don't understand. So I started giving more talks about that. In 2018, when I talked about what was going on in the twig, it was more peripheral related things, right? Like security, we had published a position paper on the persistent memory hardware security threat model. We were getting a lot more into the details of remote persistent memory and talking about other things like higher level semantics. And then last year, I went back to the slide because I realized we kept talking about these kind of gory little details, but it was important for everybody to realize that the persistent memory programming model was actually designed to be fairly simple. It is built off of the storage APIs, and that was kind of the highlight of my message last year. If you use the path in the middle there, you're just using persistent memory like an SSD. Nobody modified your file system, nobody modified your program, it just worked. It just seems like a really fast SSD. If you use the path on the right, you're just using persistent memory like an SSD with no page cache because it's got direct access. And it's not until you actually decide to use that optimized flush that I mentioned earlier that you're even using a new API. Until then, you're really just using APIs that have been around for decades. So that was a very strong message I wanted to give last year to remind everybody that the storage APIs are there and they work. So today, we're really just focused on the right-hand side of the diagram. The operating systems have named that DAX for direct access. And this will be the focus of most of the talks that you hear today, will be some way of using DAX or using this programming model. So it's a relatively straightforward programming model, we think. So where has that worked? In the past 8 years or so, where has that model actually worked out for us? Well, I would say things that build on the model have worked out pretty well, including our libraries like PMDK. We haven't had to, while building these libraries, we haven't had to go back and say, gosh, I wish this model were different. In fact, it's actually worked really well for building PMDK. PMDK is a suite of libraries. Like I say, you'll hear more about it later, and I'm not going to go into them, but they're up to about 10 libraries right now, and you pull in just what you need. But it is worth mentioning that back when I first started talking about PMDK, we had the idea in the lower left there of the volatile use of persistent memory, right? So it is persistent, but you don't happen to care that it's persistent. You're just using it because it's big. It's high capacity. The product that I have pinned to my shirt here is 3 terabytes per socket. And so it's pretty high capacity. And it's cheaper than DRAM, so maybe one of the use cases is just to store stuff there, but not worry about it being persistent. And that's turned out to be kind of wildly popular. It's one of our most popular ways of using persistent memory. And so on the left, you can see there are a couple of these libraries that one of them actually just designed over the past year that have made quite a bit of traction in the ecosystem. So this last year then, in my summary of this last year, it's been a very exciting year. Intel did actually launch their persistent memory product. You can tell, okay, now it kind of shows that I work for Intel because I wrote, Intel launches Optane DC persistent memory instead of Intel finally launches Optane DC persistent memory, which I believe you'll probably see on some other slides. And you can also tell I'm not in marketing because I forgot the little R with a circle around it. But basically, this was a pretty exciting thing for me, being an Intel employee and working on this project for a good 8 years. It's really been great to see it actually launched and shipping in the wild. But it's been an exciting year for me too, because a lot of the companies over the past few years, I came up here and I told you, I just saw this great demo of somebody showing that they could use persistent memory. You know, a lot of these big these big companies that I've been working with have now moved beyond the demo stage to the stage where they're shipping products that claim to fully support persistent memory in one way or another. There are quite a number of these right now. I'm not naming them here, but a lot of them will be, some of them anyway, will be giving talks today. So that's pretty interesting too, I think. And the number of use cases, different ways for people to figure out how to use it, and the number of ways they've decided to do software enabling have really exploded. It's actually pretty incredible. Again, you're going to hear about a lot of it today. It includes things like new people coming up with ways of using it, or even building startup companies around new ideas, ways of using persistent memory. So I think that's pretty exciting. When I started on this project about 8 years ago, I looked into academia and I looked for papers on persistent memory programming, and there were 2 notable papers that were even not that new. They had been around for a few years, and they were done as, I think, as master's thesis papers. But now I've lost count. Every year we get so many of these academic publications. It's amazing. It has really exploded. If you go to the non-volatile memory workshop at UCSD, a lot of the talks there are now about persistent memory. We've got a new conference that we did last summer in San Diego called PIRL, P-I-R-L, which is Persistent Programming in Real Life. And it was a fantastic conference. It was one of the best I've been to. And so that was pretty exciting. But it was both people talking, not just from the academic sense, but also some of their real life experiences in implementing some of these things. So it's been a pretty exciting year, I'd say, for persistent memory in 2019. So that all sounded really good, motherhood, apple pie, but you know, the model wasn't perfect, even though I tried to keep it simple and straightforward. There are always places where you can criticize what happened, and I think that's important for us to do. So where did the model fall short? So first of all, if you think back around this file system that's at the center of our model, this persistent memory aware file system. On Linux, the two file systems that are persistent memory aware are ext4 and XFS. At least these are the two that are upstream in Linux. And on Windows, it's currently NTFS that supports DAX. There are others, but they're either private or experimental, not upstream. So I'm not listing them here right now. These are the ones that are available to the general public. And so, like I said, we had this little hiccup where the Linux guys said, whoa, not so fast. I don't think we can just give you that flushing capability from user space and make it safe. And we negotiated for over a year between the Linux community, different people in the Linux community, and came up with this solution called MapSync, which is now something that the model never mentioned something like this. And we did go ahead and roll that into the next spec. We said, well, you may have to request information to use the optimized flush. And so that actually did make it into the spec. But what about an uncorrectable? So this stuff is like memory. It sits on the memory bus. You can have an uncorrectable error, right? They're rare, thank goodness, but they do happen, and you have to be able to code for them. So if an uncorrectable error happens where I've shown it in the data that the application has mapped, it's up to the application to deal with it. The application can say, I can't use this data anymore, and go get it from a backup tape. Or the application can say, oh, I've got redundant information, and I'm going to go ahead and repair the uncorrectable. But what if the uncorrectable happens down in the metadata of the file system? Usually that kind of metadata is protected by things like software RAID. But we don't have software RAID because there's no block stack anymore, right? We're just accessing the media directly. So this to me was sort of a failing of the programming model. And I went to the Nova guys, these guys who did a research file system at UCSD, and I explained this problem to them, and I said, you know, we'd really like to see replicated metadata. And you know, these are like grad students, right? They didn't know this would be hard, so they just went ahead and implemented it. It's actually pretty cool, but it's Nova. It's not an upstream production quality file system currently, but it's you know, something to be watching. And I've also discovered other ways of sort of solving this problem, like by taking XFS, where you can separate the metadata onto a different device, and you can RAID that device. But it's kind of complicated to set up. So it's sort of a failing of the model. Similarly, the Linux guys also came up with this other thing that you see on the far right of this diagram called device DAX. Device DAX is not the SNIA programming model. It doesn't use a file system. It is very powerful. It's kind of a raw access to persistent memory. People use it because it supports RDMA better than the file system DAX currently on Linux. But it is a little infuriating to use. It doesn't follow POSIX. If you open up device DAX, first of all, you have to be root. If you open it up, you can't find out what the size of your persistent memory is. Stat doesn't work. You have to use some special magic functions that we've put into PMDK to figure that out. If you write some changes to device DAX, msync doesn't work, right? You can't flush the changes using the normal way. So things like this are complicated. And we've tried to take away a lot of the complications. You can see PMDK is in this diagram, and it knows how to use device DAX, and it abstracts away those details. But the whole fact that the Linux guys even had to create this, I think, shows a failing of our model, that we didn't foresee the need here. So that's something, again, I'd like to see us go back and re-examine and decide if the programming model is missing something because of that. So ongoing work. Given all that, what are we doing in the programming twig? Well, first of all, the NVM programming twig was originally created to do all things non-volatile memory. So we were talking about disk interfaces, SSD interfaces, and stuff like that. after that first spec, we've done nothing but talk about persistent memory. So maybe we should even be calling ourselves the persistent memory programming twig at some point. We do continue to meet. Instead of it being every week, it's more about every month now. We do continue to meet face-to-face about every quarter. The chair of the twig was sitting here a minute ago, but he moved somewhere else. Where did Alan go? Oh, okay. So he went to go get ready for the next twig meeting. And, but we still have a lot of heavy discussion, a lot of interest in the remote persistent memory. Actually, the changes to RDMA are really coming along nicely, and how those work and how those will be used are one of the things we're describing. There's still quite a big interest in resyncing with the stuff that happened in the ecosystem that I mentioned, where it didn't have anything reflected in the programming model. So we're talking about doing a 2.0 programming model spec. Actually, at the meeting yesterday, we got quite a bit done in just sort of reorganizing the spec and getting it ready for that 2.0 publication. So that's coming. In the meantime, inside of Intel, a bunch of us got together, driven by my coworker, Steve Scargill, and we took all the persistent memory programming things that we had been writing and talking about for the past few years and put together a book. The book is you can get to it, it's free. If you download it and read it online, it's free. Or if you want the printed copy, you can pay for the printing costs, which are fairly minimal. But the book itself, I think, has turned out really great. So I just wanted to make sure people were aware of that. There's a little thing you can take a picture of with your phone and follow the link. It just gets you to the PDF download or a place where you can order it. So that's not particularly done by the twig, but it's definitely a lot of the same information that the twig has been working on over the years, and that we've been working on in persistent memory programming, kind of culminating in a book. So for the 8th time, there is your summary of what's been going on in the NVM programming twig. Any questions about the twig or anything I can answer in that area?